In this, we're going to delve a little deeper into probability topics. We're going to start with independent first. So let me give you a definition of independent events. Two events let's call them A and B, are independent if the occurrence of one does not affect the probability of the other event occurring. And there's a couple ways you can tell mathematically whether two events are independent or not. One is to look at the conditional probabilities like this, A/B. If they're independent, then P of A will equal that. So let me sort of explain this more. This says this is the probability of A being true given that B has already occurred. Now, if B has no effect on the probability of A, then that's exactly what's happening here. Probability of A was unaffected, so B had no bearing on that. Similarly, another thing that happens is if you switch them around, so in this case it says since A already happened, it had no effect on the probability that B would actually happen. One last thing. If you have the probability of A and B, that equals the probability of A times the probability of B. This is an example. Flip a penny and a quarter. Whether the penny, whatever happens to the penny has no effect on the quarter. So whatever happens with the penny has no bearing on the probability of, or has no bearing on the quarter. So whether the quarter is heads or tails, that has nothing to do with whether the penny is heads or tails. Let me write down a sample space for this that I think might be useful here. So I'm going to do flipping a penny and a quarter. Here's what I'm going to do. I'm going to do a P. This will be the penny. PH will mean the penny came up heads. PT means the penny came up tails. And then we've got QH, and I'll do QT. So I have four different possible outcomes here. Now, we would like to know, now as I mentioned, they're independent of each other. What is the probability of both coins being heads? So basically what I have here is I have the probability that of PH and the probability of QH. That's what I'm looking for. Now I mentioned they're independent, so I can do this. The probability of pH times the probability of QH. The probability of pH, now it's talking about a penny. Penny flip is either going to be heads or tails. You got a 50-50 shot. So that's going to be 0.5. Similarly, for the quarter to land up heads, that's also got a 50-50 shot. And together, you'll find that this equals 0.25. Or the probability is about 25% that you get both two heads. This problem comes out of your textbook. It's problems like 68 through 78 or something like that. Yeah, it's 68 through 78. Let me read through this. It says the graph shown is based on more than 170,000 interviews done by Gallup, and it doesn't matter when they took place, but the sample consists of employed Americans 18 years of age or older. The emotional health index scores are the sample space. So the scores are the sample space. We randomly select one emotional health index score. So what I'm going to do is I'm going to try to give numbers to each of these bars. So the numbers here, down here, is sort of a scale, but they don't give it any more than this. So you have to kind of estimate a little bit since I don't know the exact values. I am going to say this one right here is 79.6. Let me increase my thickness. The next one looks to be exactly 80. Oh, that's still too thin. The next one I'm going to go with 80.1, I think. Sales, then I'll go with 80.2. And then for the next one, 80.3. Let's see, what is the next one? I'm going to guess 80.7 for installation and repair. Construction or mining, I'm going to go with 80.9. Manager, executive, or official, that looks to be 81.5. That next one's tough. I'm going to go with 81.8 or 7. I'm going to go with 81.7. And then I'll go with 81.8. Of course, 0.9 probably would still work. This one I'll say is 82.3. These would be 82.7 for both of them. And then the last one, for physician, it looks like 83.7. That looks the same to me. All right. So from those numbers, I'm going to write the sample space. Let's see, we got 79.6, 80, 80.1, 80.2, 80.3, 80.9, 81.5, 81.7, 81.8, 82.3, 82.7, but I'm going to list it twice. And then finally 83.7. So let me count how many things I have here. Well, you have one for every bar, so let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. They didn't tell us it was 14, so let me just also make sure I've got 14 numbers in here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so I've got 14. Now I'm going to bring in the questions from the homework. The first problem is the probability that an emotional health index score is 87. So what I'm going to do is this. I'm going to allow the health index score, the emotional health index score, I'm going to call it by the letter E. So when I write this more mathematically, I'm actually asking you this. What is the probability that E equals 82.7? Well, there's a total of 14 to choose from, and there were 2 of them that was 82.7. So you can leave the answer as that, or if you want, I can put it as a decimal, 0.1429. I'm going to leave the even ones for homework, but I am going to leave the odd ones for homework. I'm going to do the even ones myself. So this one here says, find the probability that this E score is more than 81. So we want the probability that E is greater than 81. So I simply need to look at those that are greater than 81. You can do it from the numbers, but the picture is probably going to be easier to do it. If I look, any of these bars that go from 81.5 and higher are all going to count. So I have 1, 2, 3, 4, 5, 6, 7. I have 7 of those out of a total of 14, and you'll find that this equals 0.5. If we already know in advance that an emotional health index score is 81.5 or more, what's the probability that it will become an 82.7? So let me come up here for a second. We already know that the score is 81.5 or more. That means we already know that the score starts here. So it's these last 7 items. These last 7 numbers are all what they're talking about here. So with that said, I'm going to do something like this. Watch this. I'm going to write S prime. This is like a sample space, but it's an adjusted sample space. It's a sample space that is going to take into account just these items here. All right, so I've only got 7 items here. 1, 2, 3, 4, 5, 6, 7. Now, the probability this time the probability that E will equal 82.7 is now there's 2 of those out of a total of only 7 choices this time. So when they write this, if we know an emotional health index score is 81.5 or more, so we know that already, here's what we did. We can do, it was the probability of having E equal 82.7 given that E was greater than or equal to 81.5. So you can see they're using the phrase given that. So they're asking us this: what is the probability that an emotional health index score is less than 80.2? So we want the probability that E is less than 80.2, given that we already know it to be less than 81. So first, what I'm going to do is look at all of those items that are less than 81. So how many of them were there? Well, it was these first 7, wasn't it? Yeah, all of those. So I would like to make an S prime. That means a new sort of sample space. So I'm going to put a prime, and I'm only going to include those items which are less than 81. So all of these guys are gone. Here's my thing. So I've only got 7 to choose from. How many are actually less than 80.2? I have 1, 2, 3 of them. As a note, if 2 events are not independent, we call them dependent. Sampling. When I talk about sampling, I'm talking about something like drawing a card out of a deck of cards, or pulling a marble out of a bag of marbles, or any of the stock probability problems that we have, where you have to try to decide if the first thing you did affected the second thing. So let me I'll just say this for now. We can do with or without replacement. So I'll use the card situation as a perfect example. Suppose you pull 2 cards from a deck. So you pull 2 cards from a deck of 52 cards. Now, depending on how you drew the cards, you may or may not affect the draw of the second one. So, first card. So let's do with replacement. Okay, so this case, you pick one card, note it, and then put it back. So now the deck is returned to its former 52 cards. Reshuffle the deck. And choose a second card. So what happens here with the replacement, since I put the first card back, and shuffled, I still have 52 cards for which to pull the second card. So by putting the first card back, I've reset the game. And by resetting the game, it means the probability, any probability associated with the second card has not been dependent upon what happened on the first card because you put it back. If you didn't put it back, that's a different story. So here we can see that this is clearly independent. So the first card is independent of the second card. Now, without replacement. So you can either pick both cards at once, or you can pick them one at a time. It's just you don't put the first card back. So we're going to pick them one at a time without putting any cards back. Now this is different. These are not independent now. These are going to be dependent, because when I take the first card and don't put it back, there's not 52 cards in the deck. That means, well, there's only 51 cards. So when I talk about the probability of anything with regards to the deck that's left over, those 51 cards, all of my probabilities will have a denominator of 51, which is not a denominator of 52. So you can see this second situation affects the probability of the second thing that you do. All right, suppose you draw 2 cards from a standard deck of 52. Now, we'd like to calculate this. Let me put the probability of 2 hearts so that means that I would want a heart on the first card and a heart on the second card. So there's 2 parts to this question. Part A we'll do with replacement. And B without replacement. We'll start with A. All right, so what we want is we want a heart on the first card and a heart on the second card. So with replacement, probability of 2 hearts. So on the first card, so let's do the first card. What is your probability of getting a heart? Well, if you don't know cards, you're stuck here. I happen to have in my computer a deck of 52 cards printed out. So let me grab the picture. Here's a deck of 52 cards. Each of these rows is referred to as a suit. The first suit are the hearts, that's pretty evident. The second suit are the diamonds. The third suit are called spades. And the fourth suit are called clubs. Notice that there's exactly 26 red cards and exactly 26 black cards. These cards over on the left with the pictures, they're called face cards. And of course, here all the way on the other end are the aces. I don't need all this information just right now. All I need to know for this problem is that in that deck of cards on my first draw, there are 13 hearts in that deck out of a total of 52. So the first card I want to be a heart. And so the probability of that happening is 13 out of 52. Now this is where you take the multiplication rule that we're going to be making use of. We multiply times the number of ways of choosing the second guy. We also want the second one to be a heart. I probably should write the words because you might think if you don't look that it would be heads or tails. Well, with replacement means that I put the first card back and reshuffled. So therefore, there's still 13 hearts out of 52 cards. And if you'd like, you don't have to do anything with these fractions if you don't want to. You can just have your calculator do them. The only thing is you've got to be a little careful on how you do something like this. If you're going to do Desmos, let's take a look and see how Desmos does it. 13 over 52. So you can do 13 divided by 52 times, and do the same thing again. 13, I'm hitting the slash right underneath of the question mark. That's how I'm getting the fraction here. And notice over here it gives me to the right. If you're interested, you can also click this button to get the fraction version of it. I'm perfectly happy with 0.0625. Now, you might also use a calculator. Let me go there. And it's a little more dangerous there. Because I want to do 13 out of 52. I can't just write them however I want to. What you need to do is this. Put a parenthesis, 13, put your division, 52, end of that parenthesis, times, start a new parenthesis, 13, divide, 52, finish the the parenthesis. Then hit equals. For you, your calculator is an evolution. Now, this calculator is not really a scientific one. In fact, it says scientific, but it really doesn't work like one. When you type it into your calculator, you should really use the parentheses that are available, and it should probably look something like this. The calculator probably will not make you put a multiplication sign between the parentheses, but you want to make sure your 13 out of 52s are in parentheses. Or if you don't want to do that, you know that it's 13 out of 52 times 13 out of 52. You could also do that, take it to the second power. Now, let me go part B. This without replacement, what's the probability of 2 hearts? So once again, I'll look at the first card and the second one. All right, the first one. The first one is no different than last time. It's 13 out of 52. However, I don't put that card back, so there's only 51 cards. Now I'm making sure that the first card was a heart. So I have sitting on my desk a heart. What's left in the deck? 51 cards and 12 hearts. And if you go 4 decimal places on this one, this is what you'll get. So you can see here, these are dependent. You can see that because the probability of the second choice was changed since the first choice took a card out and didn't put it back. Suppose a bag contains 5 blue marbles, 3 red marbles, and 1 green marble. Suppose you draw 2 marbles at random. So what is the probability that the first marble is red and the second one is blue? As before, I'm going to give you 2 things, with replacement and without replacement. So part A will be with replacement. And part B would be without replacement. So start with part A. We want the first marble, so I'm going to do it this way. I'm going to go, let's see if I go probability, and so the first marble is red and the second marble is blue. So I want an RB is what I'm looking for. Well, the first one, let's say the first one is red and the second one is blue. All right, so we'll set it up. Now we're doing with replacement part A, so there's a total of 9 marbles in the bag, and there's 3 red ones. So 3 out of 9 for the first selection. Now, since you put the marble back, all the marbles are still there for the second choice. In that case, you have 5 blue marbles and 9 out of 9 marbles. And as a decimal, I got 0.1852. Now, with route replacement, the red one being first is still 3 out of 9. However, you're not putting it back, so there's only 8 marbles left for the second choice. However, there still are 5 blue marbles. This one turns out to be 0.2083. The next topic in this section are mutually exclusive events. So mutually exclusive events cannot occur at the same time. I mean, some obvious ones are flipping a coin. I can't get heads and tails at the same time. What we have mathematically, suppose let's do this. Let A and B be mutually exclusive. What that means is that A and B is the empty set, and the probability of A and B equals 0. So when you put A and B in here, you go, what's the probability that A and B are true at the same time? Well, we know they can't be, since they're mutually exclusive. As an example, let's flip 2 coins. So if you flip 2 coins, there are 2 outcomes for the first coin, and there's 2 outcomes for the second coin. That means there's a total of 4 outcomes. So my sample space looks like the following. I have heads, 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 tails. So that'd be heads first, then tails. Or I could have tails first and then heads, and then finally tails, tails. Let A equal the event of at most 1 tail. So at most means less than or equal to. So A is the event of having 1 or 0 tails. So if you were to write the set out, I just write all the ones that have less than or equal to 1 T in them. And then TT is not included in that. While we're here, I might as well put this, the probability of that event happening, well, there's 3 options there, and there's out of a total of 4. I'm going to let B equal the event of 2 tails. Well, there's only one thing that B can be. Then B is equal to simply TT. And the probability of B, while I'm here, they ask you for them anyway, so I might as well do it. There's 1 outcome out of the 4 that possible. Notice that A and B do not overlap. So A and B are independent events. Let's let D equal the event of more than one tail. Well, the event of more than one tail, there's only one option here, and that's that we have two tails. More means strictly greater than, so one is not allowed to be a part of the answer here. So the D is going to simply equal TT. Then try E. Let's say that's the event of H on the first coin. So as I write it mathematically, then HH had a heads on the first try, and then we have an HT. The other ones, though, had tails on the first try. So if you look between D and E, I can see that those are also mutually exclusive. You can see this TT is certainly not in here. All right, draw two cards from a standard 52 deck with replacement. Okay, so we're putting the first one back. Find the probability of at least one black card. So when we look, since I'm choosing two cards total, here's what my thing looks like. I could first have a red card and then a black one, or I could have a black and then a red. I could have two reds, I guess, and I could have two blacks. So any of those four possibilities are possible. Find the probability of getting at least one black. So I'm going to, my event, I'm going to call it by the letter E for event. At least one black card, then that means RB is okay. BR is okay. RR is not possible because that doesn't have any black cards, but then B is allowed. So the probability of E equals 3 out of 4. All right, they give us the fact that the event A is learning Spanish and the event B is learning German is not important at all. All I need is really this stuff right here. This is the only thing necessary in this problem is this stuff. And they want you to show one of these three to be true because any of these will show that A and B are independent events if you can show that this happens. Let me show you how the first one goes. P of A slash B equals P of A and B divided by P of B. Let me plug in my numbers in. The probability of A and B being true is 0.08. And the probability of B being true was 0.2. Well, this is easy enough to do on any calculator. Do I have it still up? I do. .4. Well, notice that's the same thing as P of A. So by doing this, by starting here and ending here, I showed the first one to be true. The second one works exactly the same way. Remember, the numerator for this is exactly the same as before. The only difference is the denominator is different here. So I'll put in my 0.08 in the numerator again, and then the probability of A is 0.4. Let's go back to the calculator. .2. That, of course, is the probability of B. So I'm doing all three of them. You only had to do one, but I'm going to do all three of them. And then finally, the probability of A and B equals the probability of A times the probability of B. Well, let's see. I have 0.4 times 0.2. So this is like a question mark. When you multiply, you might remember that when you multiply two one-digit decimals, you'll get a two-digit decimal. And in fact, it'll be 0.08, which of course equals the left side. All right, this is a try it from your homework or from your textbook. We have 6 red marbles, 4 green marbles. And so they've numbered the red marbles 1 through 6, and they've labeled the green marbles 1 through 4. So what they look at this is they go, S has 10 outcomes. What is P of G and O? Well, let's take a look. I want green and odd. That's what the O's stand for, are odd numbered marbles. G is green, R is red, obviously. But then, so if I only want the odd ones, when I talk about them, I'm talking about G1 and G3. These are the green and they have odd numbers attached to them. So in this case, there's a total of 2 out of 10. So you can do it directly like that if you want to. But now let's see if they're independent. The option of getting a green or an odd, the probability, and I think you can see that it's not going to be that way. The probability of a green times the probability of an odd. Let's see what that is. The probability of a green was 4 out of 10, and the probability of an odd is a 5 out of 10. Let's see what happens. So 4 out of 10 is 0.4 times 5 out of 10, which is 0.5, equals 0.2. Oh, I was wrong. This equals 0.2, which equals P of G and O. So they are independent of each other. All right, student goes to the library and they give the probability of whether that student will check out a book or a DVD or both. So let me use the formulas on these problems. So we'll start with A. I want the probability of B/D. So you know that this is the probability of B and D divided by the probability of D. Now give us B and D is 0.2, and the probability of D is 0.3. I know this one. This is going to be 0.6, and the 6's will go on forever. Well, you see, this is obviously, they're not independent, obviously, B and D, because this is not the same probability as B. Similarly, if I do the other way, the probability of D, given that B already happened, is the probability of B and D again, divided by the probability of B. So now we have the probability of B and D is still 0.2. The probability of B is 0.4. So this equals 0.5. Well, I've already answered. This answer was no. And are they mutually exclusive? No. How do I know that? Well, because of this. If they were mutually exclusive, that number would have been 0 and not 0.2. Another problem here, 70% root for the home team, 25% are wearing blue, and 20% of the fans wearing blue and are rooting for the away team. So here's what they've given us. 70% of fans are rooting for the home team. So I'm going to use the letter H for home. The probability of H equals 0.7. It's easier to do this. But now, what is this probability here? So what's the probability of A? Well, the question is not perfectly stated because it's making the assumption that 70% of fans are rooting for the home team, automatically the rest of the fans automatically root for the away team. And that's probably not true, but they are going to assume that, so they're going to put 0.3 for the probability of rooting for an away team. Let B be the event a fan is wearing blue, and that's right, or that says right here, that tells us that. So the probability of B is given to be 25%, or I'd put 0.25, I think, instead of 25%. Are the events of rooting for the away team and rooting for the blue team independent? Are they mutually exclusive? Well, let's start with independent first. So what I need to do is look at the probability of A/B, A given B. Let's see what we have here. I have the probability of A and B divided by the probability of B. Now this is supposed to turn out to be probability of A if everything works out well. So what do we have here? Here 20% of fans are wearing blue and are rooting for the away team. So what that means is 20% is this A, is the probability of A and B. So let me put that in. I'll go underneath of here. So 20%, I'm going to put 0.2, and the probability of B, 25%, that's 0.25. This equals 0.8. Does that equal the probability of A? So does that equal, question mark, the probability of A? Well, what is the probability of A? The probability of rooting for the away, oh, there it is 0.3. So they're not the same thing. So this answer to this part is no. Now next, are they mutually exclusive? So let's take a look at what I have to do in that case. So this was for independence, the first part. For mutual exclusivity, I look at the intersection. If it has things in it, then they're not mutually exclusive. And you look, the probability of A and B is right here. It's 0.2. So with that said, that cannot be the empty set. So we have Mark is deciding which route to take to work. He's got I, the interstate, or 5th Street, and he's got the numbers. And, well, obviously, he can only take one route to work. So let's take a look at what is the probability of I or F. And you really don't need to think very hard, although it took me a couple seconds to think about this. What is the probability of I or F? They have no overlap, right? Isn't it true that no matter what, he is going to take either I or F to get to work? That means I or F, the probability of choosing one or the other of those is 100%. Or just one. All right, let's see. We have 2 balls to choose from, white and red. We select one ball, put it back in the box, and select a second ball. So this is replacement. Let T be the event of getting the white ball twice, F the event of picking the white ball first, and S the event of picking the white ball in the second drawing. So, well, they're using S, so I can't use it for the sample space, so I'll say sample space. All I need to do is know what's in that thing. So we have white and red. So what can we do with this? We're going to select the second one. So we can have a white, white. We could have a white, red, red, white, red, red. It'll do you good if you can recognize that this problem is no different than flipping a coin. This problem is also no different than those problems dealing with the gender of a baby that's just been born. Everything in these cases is considered to be 50-50 in statistics classes. So anyways, let's see, compute P of T, what was that? T is the event of getting the white ball twice. So there's only one. So let me put T is equal to just W, And the probability of that is 1 out of 4. For part B, so that was part A. Part B, we want PT/F, probability of T/F. Let me get a handle on F. What was F? F, the event of picking the white ball first. So let's write those in there. The white ball first, we'd have W, W, and WR. Okay, we're going to assume, and then T would be the event of getting the white ball twice. So here the probability is going to be 1 out of 2, but I'm going to use the formula to get at it. So first, let's start probability of T and F divided by the probability of F. All right, so the probability of T and F, that means T is true, so getting the white ball twice, and F, meaning it was first. So both of these have white ball first. So if you look at F, then we have these items. T is WW. The only thing in their intersection is WW. So the probability of T and F is 1 out of 4. And the probability of just plain old F was 2 out of 4. So that equals 1 out of 2. And the way I was setting it before was a little bit, I'm going to say it in a little bit of a different way. Well, let me finish the problem and then I'll finish what I was saying. Let's take a look at part C. Are T and F independent? So when I looked at the probability of T/F, I got 0.5. Now what's the probability of T? The probability of T is 0.25. So this does not equal the probability of T. So they're not independent. D, are F and S mutually exclusive? So there's my F. And S is the event of picking the white ball in the second drawing. So I can get that. The S for second, I'm guessing. So this would be one of them. And then we'd have this one. And that's it. So let's take a look at these two. Are they mutually exclusive? No. F and S both have WW in common, and that's not the same as the empty space, empty set. Are F and S independent? So let's take a look. Let's do the probability of, it really doesn't matter what we can do. Let's do the probability of F and S. So they're asking me if F and S is independent. So let me see the probability of F and S. We have it right here, so that's 1 out of 4. And since, well, I got to determine whether it's independent. Now the probability of F, I'm going to do it this way. The probability of F times the probability of S, is that equal to 0.25? I don't know. Let me see what was F again. The probability of F was 0.5. And the probability of S is also 0.5. That equals 0.25. That actually checks out. So yes, they are independent.